but we have Anders from Partisia telling us about MPC as a service for everyone.
Is this the...
I'm expecting the slides to be with you at any moment now.
Let's see.
I retain my optimism. Here it is.
Here we go. And this is how it works. Okay. Hi, everyone. I'm super happy to be here. This is like a great conference. I'm going to talk about, well, my talk is titled MPC as a Service for Everyone, but more concretely what I want to talk about is this thing that is called Partisia blockchain, which is something that we have developed at Partisia. And like the short story is, it's a blockchain, but with MPC as a feature, so something that you can use. And it's called MPC as a Service because it's an MPC as a Service system. It's for everyone because it's a public blockchain, which means don't put your GDPR data on it, I guess. That was the conclusion from the last track. But let's get into it. So this is very much a talk about how this is like realized, so like the technical details. So not so much about the actual MPC protocol and so on, but more like the whole system surrounding it. But nevertheless, it's a very good starting point, as others has also done today, is to start with what is secure multi-party computation. And I've added as a service here because that's what I'm going to talk about. And when I say as a service, I mean this outsourced MPC model. And this simply means that the parties who provide the inputs are not the same parties that perform the computation. But otherwise, it's still an MPC, of course. It says here, let's be slightly more precise about the problem, and then they define a lot of things that they're not very precise about. So for example, there are some parties, there is some inputs, so there is these parties, there's somebody who performs this computation, there is a function that they all agree upon. When you talk about, and when you define MPC, you say there's some parties, there's a function, this is sort of assumed that these just exist, and they perform some sort of computation. And when you want to sort of take this into the real world and you want to implement these things, you sort of have to fill out all these missing gaps. It's not enough to just say, I have an MPC protocol, I've picked one from my favorite research paper, I've even implemented it, because you still need to figure out who's going to run your computation, you still need to figure out how they agree on what they need to compute, and in most cases you also need to figure out what they have, like what they should do with the inputs, like who should be able to provide the inputs, what should you do with the outputs? What if something goes wrong? All of these like tedious questions you have to deal with as soon as you move into industry, I guess. Okay, so in a bit more details, I guess, for this particular talk, I'm going to go through these four steps. So first of all, how do we run this MPC computation in this particular system? What protocol should we use? So we also have to, we cannot simply say that they run a MPC protocol. We have to actually, figure out exactly which one they should run. How do we express it? So somebody has to sit down and write this function. They cannot say, run a decision tree or, do some sort of secure regression or do an auction. You actually have to have some way to express that logic in some programming language. And finally, we have to figure out who should run this computation. And the last one is I think was also one of the points made when we talked about GDPR earlier, is that this is not actually easy. And the security of an MPC protocol typically just says, we assume that T out of N is corrupt, or at most T out of N is corrupt. But there's no way to like solidly guarantee that. There's nothing stopping everybody from just meeting in a back alley and exchanging, secure data on Post-it notes. But so we sort of have to come up with like a best effort, and that's what everybody does when it comes to MPC. Anyways, so and content warning. I'm going to use the word blockchain here. I guess I also already did, but I think so. For this part where I talk about how you orchestrate an MPC, I think actually this applies to many systems. Also, the MPC systems that you deploy privately, you're going to have to use something like this. Maybe it's not a blockchain. Maybe it's a broadcast or an centralized orchestrator or a decentralized orchestrator in some way, but actually a blockchain, for the sake of for lack of better word, actually, it's a very useful primitive to use when it comes to actually running MPC computations. And let's see why. So we have this guy down in the left corner here. He has written an MPC computation, so for now I assume that we have some way of expressing them. I also assume we have some way of picking, in this case, 4 nodes that are going to run our computation. And this guy, he wants to run this computation. And what he does is that he puts it on a blockchain. And why would he do that? Well, because the properties of a blockchain or a totally ordered broadcast is that everybody agrees on what is there. And if everybody agrees on what is written on the blockchain, they for sure can also agree on what function to run. And this is very useful. So they can agree on the computation. Moreover, we can use this for inputs. And now this is the part where I guess if you're took the GDPR stuff to heart, you should close your eyes. So this guy, say he has an input Y, he can package this up in some way and put it on the blockchain. Again, because now they can all get it. Here you should think about it as he performs a secret sharing, then he encrypts the secret shares towards each of the nodes, and then the nodes can read them. So now they will receive the secret shares, but downside is, of course, you have these encrypted secret shares lying there on the blockchain for all to see for all eternity, because it's a public blockchain. You can easily imagine, though, a different inputting protocol where instead of inputting a secret shares here, you put on a commitment, like a perfectly hiding commitment, and then you provide the shares directly to the server. This also works as well because the servers will be able to check that this was committed to correctly if they want to, but also you get sort of this checkpoints for the inputs on chain, so everybody agrees on the order. The upside, of course, of the first one is that this guy with the top hat and the Y as input, he doesn't need to communicate with the nodes directly. He just needs some way to be able to put a message on chain. And I think now is like a good point to also just to make sure to point out that we get an ordering of the inputs, which is super nice. If we have now an application that for whatever reason requires us to be able to say that the guy who input Y, since he inputted the value before the guy who inputs X, he should be privileged in some way. For example, we run an auction if two people bid the same value, for example, then we want the earliest bidder to win. I think you can also solve that by writing your auction circuit appropriately, but for the sake of illustration. This guy, the guy who ran the specified the original thing, he can of course also use the blockchain to say now we should start computing. So everybody agrees on when we start the computation. Again, they can read it. Now they can run an MPC protocol, which for now I just assume they also know which protocol to run, and they can write the output back to it. And this ordering is like very helpful, not only because it gives us a nice way of orchestrating the whole thing, but because this is super useful for later. It's very useful that we can see that a computation was actually started on this particular date because everybody agrees on it, and it was inputs arrived at like these particular times, and output arrived at this particular time. So we know whatever management surrounding this is like we get like a very nice audit trail in some sense here. Okay, and that was the output. So this is sort of how you would orchestrate it. It's fairly simple, but I think it's a very useful sort of like construction. And now it's time to fill out like the remaining missing parts. So that was the MPC protocol. We need a programming language, and we need a way to pick these nodes. So the MPC protocol, I would argue, at least for our case, where it's a public blockchain, it has to be robust, or parentheses, at least it has to have identifiable abort. And the reason for that is that we're never going to get any usable system if nodes can simply crash the computation and there's no penalty involved here. The case might be slightly different if you decide to run this in a private deployment where you have full control, or you have like you know everybody, and you can go out and do bug fixes and incidents report like on site at the different nodes. But at the very least, where these are like potentially distributed all over the place, we have to have a way to ensure that so long as they of course stay within the threat model, then we can ensure that they don't do anything wrong, which is exactly this robustness property. Secondly, the MPC protocol we want should have non-interactive inputs from the client, because the clients are assumed to be sort of lightweight and so on. We can't expect them to stick around and engage in some, they receive like an opening and then they broadcast a value or put this value on chain or whatever. So we sort of want like non-interactive inputs. To solve this, or to get such an MPC protocol, we can sort of take a somewhat standardized protocols, something like a DNO7 BH08 style protocol, which is Shamir secret sharing, uses triples for multiplications, has a scalable preprocessing, not super relevant because our setup currently just uses 4 nodes, so scaling doesn't really matter if n is constant. For the input protocol, it's the same input protocol, if you know how input protocols in these sort of protocols work, but with like a slight twist. So instead of the client receiving some opening of a random value, they will just provide the shares to the nodes. The nodes do the masking, then they attempt to open the value. If that goes well, then you do like the offsetting, and then you use that as the input. This guarantees that the X shares that they have in the end down there are going to be valid, and it also allows us to do like additional checks on this value M. It's mostly related or mostly needed since, and I'll get to that just in a second, I guess, but we're doing computations over a binary field, so you want to, and when you do computation, Shamir secret sharing over a binary field, you need an extension, but now you need to make sure that your shares are actually in like the base field of this extension. Otherwise things start to like fall apart in like very strange ways. So there's some checks that involve there. But in sort of the grand scheme of things, it's a DNO7 BH08 protocol that is used here. Okay. MPC programs. Okay. I think this one is like very interesting. So if we start here on the left, that's what you have when you have an MPC protocol. So either of these, or any MPC protocol for that matter, since it implements an arithmetic black box with arithmetic over some field or ring, gives you something like these operations here. Like you can add things in a finite field. You can add constants, so the b here is also a value in your finite field. You can multiply these constants. You can multiply secrets even, and you can also reveal these at some point if you wish to do so. The issue is that I would at least argue, and that comes from sort of experience in talking with people who are not experts in MPC, but also I think it makes sense that if you tell someone that, here's this super cool gadget, it knows how to multiply elements in an extension of F2, then it would look at you like a giant question mark and ask, how can I run my machine learning using this primitive? So what we actually want is something on the right. And this is like blockchain related. This is like Web3, so we want something that is written in Rust, preferably. But at the very least, we want something that is high level, something that uses, say, a 32-bit integer primitive. Because everybody knows these, everybody loves those. On the other hand, we're stuck sort of with these operations over a finite field, which nobody loves, nobody knows them even. So the big question here when it comes to these MPC programs is how do we go from the thing on the right to the thing on the left? And I think there are some interesting challenges that we sort of ran into here. But for starters, let's just talk about how we compile an MPC program. And I guess here, just to draw like sort of a parallel to or like the perspective to a previous talk, we sort of have this scenario here where somebody puts up a specification of a computation, if you will, and then at some point somebody does a computation. So unfortunately, we cannot have a more interpreter-style MPC evaluation as, for example, that was talked about in the Rossmann labs. Here we sort of, we're stuck with, this is the whole computation, now we have to run it, and the question is now, of course, how do we run this Rust code using the operations over there? And this you do with a compilation. And the way you compile a program at a very high level is that you turn this code into a circuit that you then evaluate gate by gate. This doesn't quite work for our case, and the reason that doesn't work is because the thing on the left over here has to be general enough that we don't have to force the programmer to, for example, say, I want an auction, and this auction only works for 6 people. Because what if there's 7 people or 5? So we need, for example, to know the exact number of inputs in order to do this translation. That we don't know at the initial, when we do this, when the program is uploaded, it's just some program. And if we need to know that, that means that the compilation sort of has to be deferred all the way until the inputter adds this like red exclamation mark and says, now you can start computing. And if that's the case, and if you know anything about compiling MPC programs, you'd rather not do the compilation of an MPC program as an on-chain computation, because then the whole world, or like everybody who runs your blockchain, are going to do this compilation. And you don't want that. And just for note, we have to do like everybody has to do the compilation, because a side effect of the compilation, for example, is that it tells us how much pre-processing we need. And if this is like as a service where in a Web3 setting, somebody has to pay for something, and when it comes to an MPC protocol, you pay for the number of multiplications you use, everybody has, of course, to agree on the number of multiplications in the circuit. So this has to be written somewhere that everybody agrees on. Again, that's on the blockchain, and we don't want to do the compilation there. So we cannot do this directly because that would be too expensive. So instead, we do it by like a detour. And the idea is to turn this thing on the left. Sorry, I'm a little bit direction blind. On the left here, we turn it into what we call a meta circuit. It's not really a circuit. It's actually more of a WebAssembly like intermediary representation, or like a low-level piece of code. But the neat thing is that we can let this meta circuit be somewhat agnostic to like the finite field and the protocol we're going to use, and then we can do a lot of optimizations on it. So, for example, reorder blocks so that they're a little bit nicer, rewrite certain expressions so that they work better in an MPC, eliminate dead code, all of these things like propagate constant, blah, 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 all of this stuff. And then when we come to, and then we can put that stuff in the smart contract itself, and then we can do the lightweight compilation at the end. And then we can do this simple, because that's just going through the circuit. Or we can do a little bit of optimizations there as well, parallelize layers and so on. Okay, I think this was the last one. Node selection. So that was the last thing that sort of is needed in order to get this whole system to work. And as a starting point, what we sort of have to do is be able to talk about that this node is different from that node. And not just, this node corresponds to a different address because they have a different private key than that node, because that doesn't really tell us anything about who actually controls the whole thing. So what we get is sort of a semi-permission setting where everybody can join as an MPC node, but they have to undergo like a KYC, KYB type thing. They have to, reveal who they are to some third party that sort of verifies this information and that we expect to get right. In particular, the information we are interested in here is the geographical location. So, for example, this is taken from what we currently have running in our mainnet, I guess. There is this node among many, which has a server jurisdiction that has been set to 840, which is, if you know your ISO codes, means that it's located in the US, I think. And that means that when we perform when we want to specify computation, we get this nice thing we can sort of, pick from. In this case, I said I want all my nodes to be located in Denmark because I trust Danish people. Not because I'm Danish. It's because we're running this this was on our testnet, and we only have 4 servers. They're all located in our basement. Anyways, so we can say, I want these jurisdictions for my servers. I want them to put up this collateral, so think if they have to stake a certain amount of tokens or whatever in order to be run. And then when it comes to deployment, we give these requirements plus our code to some specialized contract. And this specialized contract, all it does is that it selects nodes based on these requirements, or it attempts to select nodes based on these requirements, say it finds someone, and then it deploys our contracts for us and codes the information into the smart contract. So everybody can go and see that this particular auction is run by 4 Danish nodes, and therefore I may or may not want to participate in it. So that's what we get. There's a bit of additional information there. In hindsight, I should also have put a link to the code. Like everything here, everything that is running on Partitia blockchain is open source. I think you can derive a link for that through the documentation. Otherwise, it's gitlab.com/Partitia blockchain, I believe. So, and that's it. Or you can talk to me also. I'm here in person, and I'm there on an email that I reply to. So,
let's thank the speaker. Anders was super nice with the time, so you can ask questions. Ah, nice.
Hello, thank you for your great talk. So we discussed a bit outside as well, and I'm very interested in this compilation from the original Rust code down to the circuit. So do you have any restrictions on the Rust code? For example, like the number of loops and later, or is it all Rust?
Oh, that's a tough question. Yes, it's most certainly a subset of Rust, this thing. And quite a restrictive subset, I believe. You can branch, for example, on secret data. Possibly, don't do that too much. I mean, the branching is like a select with a secret shared bit. You can probably not loop based on like a secret, what's it called, like cutoff point or something like that. I don't remember exactly. There is some very good explanation of like exactly what the subset it is that it implements. It's definitely not, not off-the-shelf Rust for sure, but it is like a valid Rust syntax, I guess you could say.
Yes, next.
Okay, thank you very much. I have a quick question. Why exactly 4 nodes, and what challenges are there if you want to increase the number of nodes?
Okay, so I mean, there are some engineering challenges for sure. There already always are engineering challenges. Just because we pick a protocol that works for any number, of n, as soon as you sort of, it's challenging to like scale it. It does scale, for sure. You can scale it. I think at the moment there are some, again, engineering-wise challenges. There are some places where it sort of just assumes that there is 4 nodes, and if you want to run it with more, you sort of have to figure out all those places where we, for lack of a better word, accidentally just said, okay, it's just going to be 4 for now or for the foreseeable future, so we don't care too much about it. The only other place is that the finite field, as I mentioned, we use a binary finite field. We use a very small binary extension, one that supports 7 parties, I believe, for this particular protocol. So it's a binary field of size 16. And that means that if you go above 7, then we need to use a different finite field, and then it becomes a little bit. But yeah.
Thank you for the nice talk, Anders. I have a bunch of questions, but I was told to keep it short. So I just ask quickly a bit more about the communication complexity and RAM complexity, because it seems to me like you do, like RAM complexity is based on the depth of the multiplicative circuit. So I assume like for each block evaluation, you have some amount of rounds between the servers. Does that pose any issues?
I mean, it doesn't pose any issues beyond the issue that MPC is usually round bound or latency bound. I think one area where this could this compilation thing could certainly be better is this last step here. So at the moment, it doesn't do a whole lot of parallelization there. It's mostly like parallelization you get sort of as a consequence of how you compile this meta circuit. So for example, in the meta circuit, it will say I add 32-bit values. And in this second compilation, it's just like I replace my addition now with an addition circuit. And then this meta circuit will see, there's 2 additions that are independent. Now I can run these 2 additions, independently. But it doesn't do anything beyond that, because then you sort of run into the same issue again, where any super fancy, you don't want to upload an MPC computation that stalls the whole blockchain for several minutes because they have to run a very, very complicated compilation process on chain.
Thank you so much. Let's thank the speaker just one more time.